So here we've got a conversion. We want to know what temperature water boils on the Kelvin scale. Well, we know water boils at 100 degrees Celsius, and we also know our conversion. To go from Celsius to Kelvin, degrees Kelvin is whatever my temperature is in Celsius, degrees Celsius, plus 273. So we know our degrees Celsius is 100. We simply add 273 and we get our answer in Kelvin. So 373 Kelvin would be our temperature to boil water on that scale. Second question, what is the Celsius temperature of liquid helium if it's at 4.2 Kelvin? So if I'm trying to solve for C in this equation, I've got to subtract 273 from both sides. So my Celsius temperature is degrees Kelvin minus 273. So 4.2 Kelvin minus 273 Kelvin is equal to negative 268.8 degrees Celsius. Second question. Find the energy required to raise the temperature of a 3 kilogram mass of carbon from 16 degrees Celsius to 27 degrees Celsius. So we're heating up the carbon. So we're looking for heat energy or thermal energy. Sometimes they call this Q in thermodynamics. The formula is mass times the specific heat. Every substance heats up at a different rate. We know the mass. The mass is 3 kilograms. I have to look up the specific heat of carbon, and it's on a table on your course. And it turns out the specific heat of carbon is 710 joules per kilogram Celsius degrees. So it requires 710 joules for every kilogram of carbon to change its temperature by 1 degree Celsius. So let's calculate our thermal energy. 3.0 kilograms. It's got to be in kilograms. C is 710 joules per kilogram Celsius degree, and our change in temperature, it's always final minus initial, 27 degrees minus 16 degrees. Now your change in temperature can be in either Kelvin or Celsius as long as you're consistent. And when you work all that through, we end up getting a thermal energy 2.34 times 10 to the fourth joules of thermal energy to heat that carbon up. Now, the last question, the most complicated one. We've got a block of silver that's fairly warm, 353 Kelvin, and it's only 0.8 kilograms of silver, and we're going to place that into 2 kilograms of water, which is only at 293 Kelvin. So 293 is roughly room temperature. So we've got this silver. Imagine a little block of silver like this that weighs 0.8 kilograms. And it's already at 353 Kelvin. And we're going to add it. Imagine I've got this big beaker full of water. And the beaker full of water, this is our H2O down here, is 2 kilograms. And it's initially at room temperature, which is 293 Kelvin. So when I add the silver to the water, of course the silver is going to start to cool down and the water is going to start to heat up. So once again, energy has to be conserved. And we say that the heat gained, whatever's gaining thermal energy, has to be countered in order to keep energy conserved by whatever's losing thermal energy. So heat gained is equal and opposite, notice the negative, to the heat lost. So we know our formula. First of all, what's gaining heat? The water is the cooler one, and since heat always flows from hot to cold, the water's temperature is going to increase. So the heat gain side will be MC, change in temperature, and all of this will be our water data. And that's going to be equal to the heat lost by the silver. MC, change in T, and all of this is our silver data. So we can't cancel off the masses because one's silver and one's water. So when you go and plug all this in, my water side is 2 kilograms. The specific heat of water, when I look it up on a table, is 4,200. And the change in temperature of the water, we're trying to find T final. Change in temperature is always final minus initial, so I don't know T final. But T initial was 293. And all of that equals negative, and our mass of silver is 0.8. Specific heat of silver, when you look it up on your table, is 235. And the change in temperature of silver, T final, that's the same final temperature of the water. It's said to reach an equilibrium value. So that's when the heat stops flowing, is when they both have the same final temperature. Minus T initial, which is 353. So there's quite a bit of algebra here. You could divide both sides by negative 0.8 times 235 to make it a little simpler. But at some point, you're going to have to start feeding this through the equation and getting all your TFs to one side. I'll leave it to you to do the algebra, but the goal is to get all the T finals to one side, and you end up getting a final temperature of 21 degrees Celsius at equilibrium, when everything stops being released.